Okay, so now your client comes, gives you a data set. Okay, I want to emphasize that the primary goal is to always output as good a hypothesis, final hypothesis as you can for your client. Okay, so primary goal, output best G. That's the primary goal. Okay, now we know that there's this two-step process. Okay, so we output the best G we can, but that doesn't mean that we only look at the in-sample error. So we would like to understand what is the out-of-sample error of your final hypothesis. So you can think of that as a secondary goal. It's important, but it's really ideally you want to give the best hypothesis and then also an estimate of the out-of-sample error. So secondary goal. Okay, estimate E out of G. Now the main reason why we estimate E out of G, okay, is so that we know whether or not we succeeded. And if we succeeded at the end, we are going to deploy G. So we want to deploy the best thing that we can deploy. Okay? And now I want to emphasize that validation is addressing this secondary goal. The primary goal still always remains. And I'm going to now show you that we can achieve the primary goal while still maintaining the whole validation setup. Okay, so we'll call this restoring the data set D. Restoring Dn. Okay, so basically, we're not going to output the deficient hypothesis. Okay, we're going to always output the final hypothesis G. Okay, so you have your data set Dn. Okay, so let's review what we did with the validation. Okay, so you split it into a training set Dn minus k and a validation set Dk. Okay, good. Okay, then you get the deficient hypothesis by running your hypothesis set and algorithm on the deficient training data. Okay, so you get G minus. And now what you're going to do is you're going to evaluate G minus on dk and get eval. But eval is for G minus. And we know that eval is approximately equal to E out of G minus. Okay, good. And you can arrange this by suitably choosing k, and we gave you the rough rule of thumb that you should choose k about approximately 20% of your data. So 80% for training. That gives you a pretty good G minus, and then 20% for validation. Okay, and so the output here is going to be eval. Okay, now you're actually not going to give your client G minus because you know it's deficient. Why would you give, even though you have an estimate of its out of sample error that's pretty good, okay, why would you give the guy G minus? So you're going to train on all the data and produce your final hypothesis G. Okay, and this final hypothesis G has an E out of G. Okay, so you can think of all this validation as going on behind closed doors. So the client gives you the data. At that point, you go behind closed doors, okay, and you do your business, okay, and output G, okay, and eval. Okay. And then when the client says, well, what did you succeed? You say, so you have to give them an estimate of E out of G. Okay, and so what you'll do is you'll give them the validation error as your estimate of E out of G. And what we need to do is now we need to look at whether that's a good idea. So you are going to give them E out of G equals to eval. Okay. But remember that eval was tailored to estimate E out of G minus. So we're going to come back and we're going to analyze this now. Okay. This process where you produce the final hypothesis as you would have normally done, and then you do the validation solely for the purpose of estimating E out. Nothing else. It's not to output G minus, it's to estimate E out. So take that in. That's important. Okay, so using eval to estimate E out. Let's analyze that a little bit, and let's first see also what are our alternatives. So using eval to estimate E out of G. Okay, so the VC analysis, let's go back to the VC analysis, which said we don't need to do any of this stuff. We've got G, we've got a bound. The VC analysis says E out of G, is less equal to E in of G. This also we can compute, E in of G, if we wanted to, plus this error bar, which was order of the square root of, dvc over n log n. Okay, so we always have that. But now we're doing something interesting here. Okay, we're doing validation, and so we're going to estimate E out of G using the validation error. But what is the validation error? The expected value of the validation. So the validation error is estimating E out of G minus. Okay, but this is a deficient hypothesis. Okay, now although it's possible, if you're it's possible that the deficient hypothesis is better than the full hypothesis. What that means is that when you learned on a smaller data set, you produced a better hypothesis. It's possible to construct scenarios like that. You have to really contort. So if you're in a machine learning setup where fewer data points gives you a better hypothesis, it's time to get out of that game and go and work at McDonald's. Okay, so we're all in over our head when more data doesn't result in a better hypothesis. So it's reasonable to sort of say that the out of sample error of G is going to be less than or equal to the out of sample error of G minus, because this guy is deficient. Okay? So E out of G is going to be less than or equal to E out of G minus. Okay? And indeed, there's going to be some slack here, and let's see what controls that slack. Okay? Well, if K was small, okay, then this slack is going to be very little. So then these two will be very close to each other. If K is very small, the deficient hypothesis will be very close to the final hypothesis trained on all the data. And so these two out of sample errors will be close. Okay. So here, this is controlled by, K, and K small makes this tighter. Okay, but now, what is E out of G minus? We're using the validation error, and the validation error is a K sample estimate of the out of sample error of G minus. Okay, but G minus is just a single hypothesis, so we can use the single hypothesis Hufting error bar. Okay, so the validation error is an in-sample error in some sense. We're in a verification setting where the validation error is attempting to verify G minus. So this guy is going to be less equal to eval plus order of 1 over root k, or square root of 1 over k. Okay, and that's the single hypothesis Hufting error bar with a data set of size k used to verify. Okay, and so, the question is, which is better? So when do we get a better bound? Now, it's possible for either of these bounds to be the better bound, and you always have access to this bound, and now we have this bound, and very often in practice, this bound wins, because DVC can be large. Okay, so DVC over N can be large, whereas 1 over K is, the size of the validation set, which you can make, it's proportional to N, it's 1/5 of N. So, as long as DVC is bigger than 5, this is sort of winning. Okay, so this tends to be a better bound, okay, for E out of G. Now, why is it a bound? Because E out of G is less equal to E out of G minus, and E out of G minus is less equal to this from the single hypothesis Hufting error bar. Okay, so this is sort of the comparison of the two bounds. Very often this wins, so this gives you a better estimate of E out, and then you have a better way of saying, did I or did I not succeed? Okay, so that's validation used to estimate the out of sample error. Okay, and now we'll erase. Okay, and if we accept, well, we always have the VC error bar, but if we accept that validation is a good estimate for the out of sample error, then one of the most popular users of validation is for model selection. So let's come back and discuss model selection. Let's erase first and talk about model selection.